Hi everyone. So I'm going to make a quick video just going over some examples that are going to be useful for the test. And basically what I'm going to do is I'm going to read through the outline and just talk about some of the most important stuff, in particular going over examples that were similar to the Kahoot, right? So anytime we stopped the Kahoot, just because not everyone was able to get the questions correct, and we went over those examples on Jamboard. I'm going to do a similar thing here, just as additional practice, because I do want everyone to do well on the test the very first time. So my resource I'll be using is what I posted on Google Classroom, right? So all the outlines for all the classworks, all in one document, okay? So I highly recommend just glancing through that, as it'll be very useful. But also this video is to kind of, as additional help. So anyways, I already started on the first take, but it was kind of messed up, so I just kept all this up on the board. So basically, the first main idea we covered for the term was electrostatics, right? So that's like electricity at rest. It has to do with, basically how charges work and how they interact with each other. Okay, so one thing to note, there's two types of charges, right? You have positive charges and you have negative charges, okay? So we're going to be looking at the proton and the electron, right? So the proton, we all know that these are subatomic particles, right? All atoms are made of protons, neutrons, electrons. But basically the proton is positively charged and the electron is negatively charged. Now, a rule that you need to know is that opposites attract, right? So opposite charges attract, like charges repel, all right? So if you have an electron and you have a proton, they're going to attract each other, okay? Because they're opposite charges. You have a negative, you have a positive, they attract. Like charges repel, okay? So if you have positive, positive, right? So proton, proton, they repel each other. Electron, electron, they also repel each other. Another thing to note, charge is conserved, okay? You can't create or destroy charge. All you can do is transfer charges. And speaking of transferring charges, let's look at an example of a neutral object here. So here we have a neutral object A. The reason why it's neutral is because there's 3 protons, 3 electrons, and those charges, they basically cancel out, right? So you have 3 positive charges, and then you have 3 negative charges of equal magnitude. So now let's say you transfer the charge, right? So what happens if you transfer the charge? Okay, so if we transfer charge, okay, so what happens? Okay, so this here is, let's say we're going to transfer some charges to object B. Okay, and object B, I'm not going to put any protons and electrons or anything like that. I just want to demonstrate why, when one object becomes positively charged or negatively charged, why the other object essentially becomes the opposite. So let me explain. So let's say here that I'm going to transfer 2 electrons. So I'm going to transfer 2 electrons into object B. All right, so when we look at the situation, all right, so I'm going to draw like a dotted line to separate the 2 objects. Okay, so now 2 electrons are going to move from A to B. All right, so if that happens, well, A is only going to have 1 electron, right? And it's still going to have its 3 protons. So it still has its 3 protons. 1, 2, 3. Okay, so the net charge of object A is going to be positive 2. Because it lost 2 electrons. And those 2 electrons went into object B. Right, so again, this is object A, this is object B, okay? And B took those 2 electrons. All right, so here we have 2 electrons. All right, and it's going to have a charge of negative 2. Okay, so it's important to note that when you're charging an object, say you charge an object through friction, okay? And you have something that's positively charged, let's say you have something that's neutral, okay? And you move charge from one location to the other, from object A to object B. What you end up with is, even though I only moved the electrons, okay, now object B is negatively charged, okay? That means object A has to be positively charged because it left the protons behind, okay? So yeah, that's pretty much it. That's the idea of charging, the fact that you could have 2 neutral objects, and if you're charging, right, one object, right, with the other object, then you're going to have a transfer of charge. But the original object's going to end up positively charged, right? So if you transfer electrons from A to B, B is going to become negatively charged, but A is going to become positively charged. All right, that's pretty much it. I want to try to get to circuits because that's really the most important one. All right, so we know that charge flows when there's a potential difference. Again, I'm just reading through the outline and just focusing on the most important stuff. Okay, so conductors and insulators, we'll talk about that. Electrical resistance, Ohm's law. All right. So let's get into all of that. So let's see here. So conductors and insulators. Okay, so now we're talking about electric current. So conductors and insulators. Right, so we have conductors and we have insulators. Right, so conductors, they conduct electricity. Right, we're going to focus on electricity. Okay, so some examples of conductors, metals, right? So think of metals when you think of conductors, okay? So most metals are good conductors, good electrical conductors. Insulators, charge cannot flow easily. Charge does not flow. Now I say easily just because, well, I mean, at some point, if you keep increasing the voltage, eventually you're going to get charge to go through pretty much anything, right? So like lightning can, send electricity through a tree, right? That's because the voltage is ridiculous. But generally speaking, something like wood, okay, wood's an insulator, all right? Charges cannot flow easily through wood, but they can flow really easily through stuff like, copper or iron, okay? For insulators, classic examples like rubber, okay, so we can do like rubber, wood, right, stuff like that. Those are insulators. Okay, let's see, what else we gotta cover? All right, Ohm's law. So with Ohm's law, all right, I'll just do both Ohm's law and the power equation at the same time. Those two equations are fairly important. All right, so with Ohm's law, right, so Ohm's law. Okay, so we know that V is equal to I times R, right, where V is voltage, right, is equal to the current times resistance. Okay, and then we know that for power, P is equal to I times V. All right, so power is equal to the current times the voltage. Okay. So yeah, I think there was one problem that people were struggling with, or at least I think it has to do with the order of the problem. It was the one on Kahoot with I think it was a 30-watt light bulb. So actually, I'll go over that problem one more time. So let's look at the 30-watt light bulb. Okay, so if you have a 30-watt light bulb at 120 volts, all right, so 30-watt light bulb at 120 volts. Okay, I think the first step was we had to find current. So find the current through the bulb. Okay, so we're trying to find the current. So basically, you need to know that, and this is going to be on the equation sheet, but you know that watts is a unit of power, and volts is obviously a unit of voltage, okay? And so finding the current, honestly, you should just memorize these equations, but just so you know, look at your known values and your unknown values, and you can see based on the equations how you need to rearrange it to solve for your unknowns, okay? So I know I have the power, right? My power is equal to 30 watts. Okay, I know that the voltage is equal to 120 volts, right? And so I just need to find the current. So if P is equal to I times V, all right, I can rearrange this equation to solve for I. So I know that I, if I divide both sides by V, I end up with P divided by V, okay? And then you just solve for I, right? So I have 30 watts divided by 120 volts, and I end up with 0.25 amps. Okay, 0.25 amps. That's the current going through the light bulb. Here, let me just make sure this is all still running. All right, perfect. And then I think the second part was you have to find the resistance. All right, so now that we know the current, we have to find the resistance. All right, so for this, we're going to use Ohm's law. All right, so I know that Ohm's law is V is equal to I times R, right? So basically, I just need to solve for the resistance. So to solve for R, I need to divide both sides by V, right? R is equal to V divided by I, okay? And so, yeah, we have 120 volts divided by 0.25 amps, okay? And that comes out to 480 ohms. All right, that's how you do that one. All right, so yeah, basic example. All right, so now let's start going into currents. So, all right, AC versus DC. I think that's next. Yeah, direct current versus alternating current. So just know alternating current is electricity that repeatedly reverses directions, and direct current is the current just flows in one direction. So yeah, let me just write that up. Oh, actually, before I do that, one more thing about Ohm's law, because that wasn't necessarily in the outline. We got to talk about ohmic versus non-ohmic. Okay, that's important. All right, so again, with Ohm's law, all right, we're going to talk about ohmic versus non-ohmic. So ohmic versus non-ohmic. And if you remember, we had a lab where, this is another question that not everyone was able to get. But basically, let's say you plot the current and the voltage for the resistor and for the light bulb. Okay, so basically here I have the resistor. So we took a bunch of data points, if you remember, with that lab, and with the resistor, it all came out in a straight line. Right, so the resistor, it was like this. It was linear. Okay, so this is a resistor. Okay, this is linear. It's a straight line. Okay, and then we had the light bulb. Right, if you remember, the light bulb, at the first few data points, it was pretty much linear, but then it started to like trail off. Okay, so basically it looked like a curve. Okay, so this here is a straight line. This here was the light bulb. Okay, so the light bulb. Okay, this was non-linear. So again, just so you know, for linear, you're dealing with a straight line. Okay, so linear, it's when you have a horizontal line, not a horizontal line. You just have a straight line. Okay. So a nice straight line, that's linear, okay? And a non-linear is, well, if it's not a straight line, if it's a curve. Right, so say I have something that's non-linear, you're gonna have something that either curves this way or curves that way, something that's non-linear, okay? Just not a straight line, right? So let's say it curves this way, okay? So yeah, basically the reason why the resistor is ohmic is because it obeys Ohm's law, okay? So if you're ohmic, basically that means that you obey Ohm's law. You obey Ohm's law, right? V is equal to IR, okay? Another way to think about it is you have a constant resistance, right? So a constant resistance, okay? So, for a resistor, whenever you take the voltage divided by the current, you're always going to get the same value for the resistor, right? We saw that when we did the experiments and we took all the data points, that the resistance pretty much stayed the same. For the light bulb, that wasn't the case. As the voltage increased, the ratio of the voltage to the current, right, was actually increasing, right? So basically the resistance was increasing for the light bulb. And the reason for that is that for the light bulb, as you kept increasing the voltage and more current was flowing through it, it was basically heating up, right? So the light bulb was getting really, really hot, the filament inside the light bulb. And when that happens, it actually changes the resistance of the material. So that's something that you need to consider, right? So basically, the light bulb was non-ohmic. And the reason we know that it's non-ohmic is because it's nonlinear, right? So for ohmic, it's linear. When you graph it, again, you have to graph it with current with respect to voltage, or vice versa, voltage with respect to current. So if you make that graph, looking at Ohm's law, if you have a constant resistance, it should be linear, okay? For non-ohmic materials, it's going to be nonlinear. Okay, it does not obey Ohm's law. Okay, that's the basic idea. The resistance changes. So just remember that experiment we did with the light bulb and the resistor, right? Understanding ohmic versus non-ohmic. So we'll talk about AC/DC, and then we'll get into circuits. And then I'll do an example with a complex resistor combination. Okay, so with AC/DC, right? So AC versus DC. I'll just cover all the main ideas behind it. So for direct current, if I plot the current over time, okay, here I'll put it in a different color. The direct current is going to be horizontal, okay? So the current doesn't change with respect to time. All right, AC versus DC, this is direct current. All right, so basically the current flows in one direction. Current flows in one direction, right? It's constant. You have a constant horizontal line. All right, so it's constant. Okay, with alternating current, with AC, so AC here, same graph, right? We have current with respect to time. All right, and we're going to see that with AC, it actually oscillates back and forth. Okay, so that's the key thing with AC, that it oscillates back and forth. So alternating current. Okay, so it oscillates back and forth. And you don't have to say it exactly that way. You understand the idea, right? It goes up and down. Okay, you're gonna have positive voltage or positive current going one way, current going the other way. Basically, it just vibrates back and forth. Okay, so here in the U.S., it's the standard is 120 volts AC with 60 hertz, right? So basically, if you could zoom in on the electrons inside of the wires in your house, you would see that, you know, if the circuit's on, the electrons are actually vibrating back and forth about 60 times a second, right? That's what that means. And then at the very end, we'll talk about why we use AC, right? So what's the point? That has to deal with transformers. Actually, I'll just write that down. So we use AC. So we use alternating current for energy distribution. Because it's easy to increase / decrease the voltage with a transformer. Okay, the voltage with a transformer. Okay, so yeah, basically that's it. So the reason we use AC is because you can increase the voltage to very, very high voltage for distribution, for sending the electricity out, you know, all throughout the city and from state to state. That's the whole electric grid. And then you can step down the voltage for the consumption of the electricity at the, you know, municipal level, right? So the voltage of the electricity in your house is only 120 volts, but we saw from the lesson that, you know, the voltage for like the really long distance transmission, that could get up to 1,000,000 volts, right? Hundreds of thousands of volts. So yeah, in order to do that, you need to use a transformer. So we'll look at the equation for a transformer at the end, but for now, let's get into circuits. So here, let me make sure I didn't miss anything. Yeah, we talked about power, battery and bulb, circuit, series, parallel. Okay, so let's just get right into it. Okay, so for a series circuit, just make sure you know that they have to have the same current. Okay, so any devices that are hooked up in series, they have to have the same current. Okay, so let's say here we have 3 devices, 3 resistors, they're in series. Then you have to understand that the current going through them is going to be the same. We're not going to do any problems where you have to actually calculate the individual currents or resistances for, currents and voltages for individual resistors. That's a bit much. But you need to know how to find equivalent resistance, all right, especially for complex circuits. So one example that we saw that tripped some people up was what happens if there's a break in the device, okay? So let's say that one of the device breaks for, resistors in series, right? I say these are all light bulbs and the middle bulb burns out. Well, then the whole thing burns out, okay? And the reason why is because, well, there's no longer a path for the electricity to flow, all right? So they're all going to have the same current, okay? So if the middle bulb burns out, then everything burns out for series. For parallel, oh, actually, and one more thing about series is that when you're finding the equivalent resistance, so for resistors in series, the equivalent resistance for resistors in series, you just add them up. So Req is equal to R1 plus R2 plus R3 ... All right, so resistors in series, you can just add them up. So for parallel, resistors in parallel, so one thing that's important to know for resistors in parallel is that there's a junction, okay? So basically the wires have to split up into multiple paths and then recombine. That's how you have resistors in parallel. And one thing that could happen with resistors in parallel that gives it a clear advantage over resistors in series is that if one of the devices breaks, then it's no big deal because there's still a path for the electricity to flow, right? So say you had a bunch of Christmas lights. If all your Christmas lights were wired up in series, as soon as one bulb goes out, the whole thing turns off. All right, and then you can't even figure out which bulb is actually out. That's what makes it even more annoying. But for resistors in parallel, if one of the bulbs go out, that just means the electricity doesn't flow through that branch. Okay, so in this case, I have multiple branches. Okay, say I have 3 light bulbs. If the middle bulb burns out, the other 2 stay on. Another thing to know is that for parallel, the resistors in parallel, they have to have the same voltage drop. Okay, so say I have like 9 volts over here and I have 0 volts over here. The voltage drop from 9 to 0, it's the same for all the resistors, right? So basically everything here is at 9 volts, everything here would be at 0 volts, so it goes from 9 to 0. Whereas for series, it doesn't work that way. So yeah, parallel, same voltage. For series, the voltage has to drop across each one, right? So say for example, these were all the same resistance, and we have to go from 9 volts all the way down to 0 volts. It'd go 9 volts, 6 volts, 3 volts, 0 volts, okay? Whereas in parallel, just, the voltage drops across all of them at the same time. So yeah, I also put the current splits. So make sure you know that the current splits. And then when you need to calculate the equivalent resistance for parallel, make sure you know that you have to add the reciprocals. Okay, so 1 over R1 plus 1 over R2 plus 1 over R3 All right, dot, dot, dot. All right, that's resistors in parallel. That's how you solve for them. So now let's just do a complex circuit. Again, with equivalent resistance, that's basically just how you add up the resistors. Okay, so say you attach a battery to these three resistors in parallel. Well, the equivalent resistance just means that it's going to be the same load on the battery, right? So like say that you have, three ohm resistors, right? So it's 3 ohms here, 3 ohms here, 3 ohms here. When you do the math, the equivalent resistance is going to be 1 ohm, okay? Because 1 over 3 plus 1 over 3 plus 1 over 3, that equals 1, and then you flip it and you get 1 ohm. So basically, with this circuit, you have three ohm resistors. The battery, the amount of current going through the battery, through the load, is going to be the same, whether or not you have three ohm resistors or if you have one ohm resistor, right? So that's what the concept of equivalent resistance is telling you. You're basically simplifying the circuit so that you can figure out what the current through the source is, right? So if you have a battery and you want to find the current through the battery and you have all these resistors, well, you have to find the equivalent resistance of the whole circuit. And yeah, let's do the example with a complex circuit. So I'll do a similar example to the one in class, but I'll work through it step by step and have slightly different numbers. Okay, so let's see, what's an interesting circuit? All right, say I would do something like this. So say we have a 9-volt battery, okay, and we'll have one resistor in series. We can do, I want to do 2 sets of parallel lines so that we can really make sure we understand it. Say we have these two in parallel. Then we can have another one here. And then I'll throw in another one over here. All right, so that's, adequately complicated. Let's throw in some numbers. Let's say we have here 12 ohms and 6 ohms. And then this one, I'll make it 2 ohms. And then for these, I can make this 4 ohms and 8 ohms. Okay, so this is obviously going to be, it's going to take many steps, but hopefully we get the principle of how to find the equivalent resistance for a complex circuit, because I'm not going to give you anything that's any more complicated than this, because that's already kind of a bit much. So basically, how do you approach this problem? So I have a 9-volt battery and I have all these resistors all set up. What's the approach? Well, basically what you want to do is you want to look at all your junctions, okay, which is where the wire splits up and recombines. So for example, this 2 ohm resistor, it's actually in series with the battery. And the reason I know that is because there's just one wire connecting the battery and the 2 ohm resistor, right? So what I recommend doing is when you have a schematic like this, you want to see, kind of like imagine how the electricity has to flow through the system. So I see the electricity is going from the positive of the battery, it goes through the 2 ohm resistor, then it has to split up, okay? So because it splits here and recombines here, these are the junctions, okay? So the wire splits into 2 separate lines and then comes back together. So I know that these 2 are in parallel, and that's actually the first step I'm going to do. So I know that these 2 are in parallel because there's a junction, okay? Then the electricity is going to go from here to here, and then it's going to split up again. All right, so actually, well, it splits, recombines, and then it splits and recombines. Okay, so my other junctions are here and here. All right, so because I have the junctions here, I know that these 2 are in parallel. These are also in parallel, okay? And what I'm going to do both at the same time. So I'm going to solve for these 2 in parallel, and I'm going to solve for these 2 in parallel. I'm going to color code it so we don't get lost, right? But I mean, this is just how you approach these problems. All right, so we have the 12 and the 6, right? So we know parallel, you have to use this equation, all right? So 1 over the equivalent resistance. Again, it's just for these 2, right? So I'm simplifying these 2, and then I'm simplifying these 2, and then I'm going to do the whole thing. So I have 1 over 12 plus 1 over 6. Okay. Now with these, you need to have common denominators, right? So when you're adding fractions, you have to have common denominators. In this case, the common denominator is 12. So 1 over 12 plus 2 over 12, right? So I had to rewrite 1 over 6 as 2 over 12. And then when you have a common denominator, you can just add up the numerators, okay? So 1 over REQ is equal to, well, 1 plus 2 is 3. So we have 3 over 12. Okay. What I recommend doing is flipping it before you actually simplify, so you don't forget that step. Basically, what I mean is we're solving for REQ, right? The equivalent resistance. We're not solving for 1 over the equivalent resistance. We're trying to find the equivalent resistance. Some people, they like to cross multiply, right, when they're dealing with these two fractions. Personally, the way I think of it is I just take the two fractions and I flip them, right? Because if you have two fractions that are equivalent, that are equal to each other, and you flip them, you're going to, the equation still works, right? So say you have 1/2 is equal to 2/4. Okay, well, if you flip both fractions, 2 over 1, that equals 4 over 2. Okay? Okay, so let's see what we got here. So we have 3 over 12. So if I flip the fractions, right, REQ over 1 is going to equal 12 over 3. Okay? And then I just solve for REQ. 12 divided by 3, that's just 4. All right, so here in blue, REQ is equal to 4 ohms. I'm just going to underline it because that's not the final answer. That's just solving for these two. All right, so now these two, the 4 and 8, let's go through this. So I have 1 over 4 plus 1 over 8. Okay, what do I get? Well, I need to have common denominators, right? So then I have over here, I have 2 over 8 plus 1 over 8. That's 3 over 8. Okay, and then I flip the fractions, right? So REQ over 1 is going to equal 8 over 3. Okay, and yeah, so basically that comes out to 2 2/3, which is 2.67. On the test, any circuit problems we give you are going to be nice, round, neat numbers. You're not going to have to use a calculator. Although technically for this, you don't really have to use a calculator, but just so you know, the numbers are going to be nice and neat. So again, so with this, I have these two resistors that are in parallel, 4 and 8, right? You just set them up like this, okay? Then you have 2 over 8 plus 1 over 8, that's 3 over 8, and then you flip the fraction, and you have equivalent resistance is equal to 8 over 3, 2.67. And now let's finish up this problem. Okay, so basically, now I know that these two are the same as a 2.67 ohm resistor, and these two are the same as a 4 ohm resistor. So if I redraw the circuit, right, again, I have a 9-volt battery, right, and then I have the 2 ohm resistor, okay, and then there's another resistor here, okay, and then there's this resistor. Okay, and we just saw that, well, the 2 ohms, we haven't dealt with that yet. Okay, then we have the 12 and 6 ohms, that came out to 4 ohms. Okay, and then simplifying the 4 and 8 ohm resistors, that comes out to 2.67. Okay, yeah, so now this is easy because they're all in series. Right, so how do I know they're in series? Well, there's just one wire, right? There's one continuous wire. There's no breaks in the wire, or at least there's no junctions, right? The wire's not splitting up into multiple paths, right? So if there's only one path, they're in series. Okay, so these are all in series, and if they're in series, well, you just add them up. Right, series is easy. You just add them up. So 2 plus 4 plus 2.67. 2.67. Okay, and that's 8.67. Is 8.67, and that's actually your answer, right? Because that's it. You just have these 3 resistors, you add them up, and then you're done. So 8.67 ohms. This is 9 volts. Yeah. So yeah, basically, again, the way to approach these problems, I recommend seeing how the electricity flows through the circuit, right? So understanding that it has to split up here, the current, it has to split here and then recombine over there. Okay, so that's how I know these two are in parallel. And then the same thing happens over here, right? The electricity, it splits up. It has to go through these resistors, okay, and then it comes back together. So I know that these two lines are in parallel, right? So these resistors have to add them up in parallel. This resistor is actually the 2 ohm resistor here. That's actually in series with the battery because, you know, the wire doesn't split up. It's just one continuous wire, right? So then after I simplified that, I ended up with this, okay? And again, I have one continuous wire. There's no junctions. So you just add them up in series and that's it. Let's say that I wanted you to find the current through the battery. So find the current through the battery. Okay, well, I know that I have R, okay? So the equivalent resistance, that's basically, I took this circuit, I simplified it down, and the battery, you know, is gonna see that the equivalent resistance, the total load on the battery is 8.67 ohms, okay? So we have a 9-volt battery. So using V equals IR, okay, we need to solve for I. So I know that I is equal to V over R, right? Divide both sides by R. And we end up with, what do we have here? All right, it's a 9-volt battery, so 9 volts divided by 8.67 ohms. Again, that's not the neatest number in the world, but what does that come out to? I'm trying to think. All right, for this one, I'm just gonna use a calculator. All right. So again, you're not going to need a calculator for the test because everything's pretty easy. But for this random example I just came up with, the numbers are not nice and neat. So obviously this is going to be slightly greater than 1, but I just want to get the exact value. So 9 divided by 8.67. Okay, 1.038. Okay, you could say it's about 1 point. So I is about 1.04 amps. Okay, just 1.104 amps. Okay. Again, if the numbers were nice, let's say the resistance was, 3 ohms. All right, the equivalent resistance was 3 ohms. Then it's 9 divided by 3. That comes out to 3 amps. That's not terribly difficult. So yeah, anyways, that's pretty much it. The most important part is knowing how to analyze the circuit, right? So how do you take a circuit? How do you break it down? Figuring out what's in parallel, what's in series, and then just actually going through the process. And also double check your work, okay? So when you're working through it, make sure that you don't make any mistakes, okay? You want to double check your work. All right, so what else we got? We talked about that. All right, magnetic fields, electric currents and magnetic fields, electromagnetic induction, transformers. Okay, so I'll just do one example with transformers, okay? So it has to do with the coils of wire. So I'm gonna erase this now. Let me make sure this is still going on. Yep. Okay, so if I remember correctly, the one problem from Kahoot was, I think it was 100 turns, right? So, so say we have a transformer, okay, and we have the primary voltage. All right, so the primary voltage is 120 volts. And the primary has 100 turns. remember, the secondary had 20 turns, right? So the secondary coil has 20 turns, and we need to find the secondary voltage. All right, so find the secondary voltage. So as a quick reminder, with a transformer, basically what you have is a certain amount of turns of wire, right? So here I'll put the primary in one color, right? So you're going to take the turns of wire in the primary, okay, so this is the primary, and then you have the secondary, okay, so let's say the secondary has, in this case it has less turns, but, right, this is your secondary. The total number of turns, right, don't really matter. All that matters is the ratio. So the way that the equation for the transformers, basically, you have the voltage at primary, right? So the voltage at primary divided by the number of turns. Okay, that has to equal the voltage at the secondary divided by the number of turns. Okay. Again, the way a transformer works, basically, you know, we know that an electric current can create a magnetic field, and a magnetic field, a changing magnetic field, can create a electric current, right? So, you know, basically this is also why you need to have alternating current for transformers to fundamentally work, is that the electricity has to change, right? So the current has to be changing, has to be going back and forth in order to create a changing magnetic field, which then creates a changing electric current, right? AC current on the output. And so what's interesting is that basically this ratio of the number of turns, okay, so the number of turns at the primary, okay, and versus the number of turns of the secondary, that ratio is the same as with the ratio of the voltages, okay? And if you think about it, that kind of makes sense. The primary, the more coils of wire you have for a given current, okay, the more coils you have, the more magnetic field you're going to generate. It's going to go through this iron core, and that magnetic field is going to then go through the secondary, right? So the more turns of wire I have on the secondary, the higher the voltage, right? The higher the voltage you're going to induce. So just follow this ratio. So basically, so the primary has 100 turns. The voltage of the primary is 120 volts. Okay, so I have 120 volts for the primary. I have 100 turns, and that has to equal the voltage at the secondary, right? So that's the voltage at the secondary divided by 20 turns, okay? And yeah, so you just multiply both sides by 20. So here I have, here I'll just put volts, okay? Personally, the way I think of it is I just look at the ratio of the number of turns, right? So basically, I know that I have, you know, if I have 100 turns at the primary and the secondary has 20 turns, the secondary has 5 times less turns than the primary. So the secondary voltage has to be 5 times, you know, lower, right? So if I have 120 volts, then, you know, 120 divided by 5, okay? And that's how you end up with, wait, was it by 5? Did we say 24 or 20? I'm trying to remember. Yeah, this comes out to 24 volts. Okay, so yeah, if you do the math here, basically what you have is, so 1.2 volts, right? 120 divided by 100 is 1.2. So you're going to take that times 20, okay, and that's going to equal your voltage. So 20 times 1.2 volts. Okay, so 20 times 1.2 that comes out to 24. So that's the voltage of the secondary. And yeah, that's pretty much it. So let's see, what else is there? We talked about magnetic fields. Let's see here. Yeah, everything else everyone's pretty much able to get. The biggest thing was the circuits, right? So make sure you know how to analyze the circuits. And then, yeah, you can look through the Kahoot again if you want. The link also brings you to a self-paced version of the Kahoot, so you can go through it again and see if you're able to get all the questions right. But yeah, that's pretty much it. Just make sure you're comfortable with the compound circuits, and with that, you should do well on the test. Okay?